Welcome everybody. Thanks Igor for the introduction. As he has said, my main activity is now into the Nomad project, but this morning I will talk about statistical mechanics or computational statistical mechanics, meaning more configurational. Is it switched off? Oh, okay. Is it better? Yes. No. I don't feel any difference. Do you hear better now? Yeah, okay. Right. While on Monday, I will talk about machine learning methods, and then in the afternoon we will have a tutorial on the application of some machine learning methods together with Matthias Rupp. That I don't know if here. Okay, let me start with the scheme that you have seen in different layouts many times, I guess, this week, and I think you will see again. That is the usual justification or the general embarrassment when we do atomistic calculations, then that we may devote a lot of time in having methods for calculating the potential energy surface to the maximum possible accuracy. But still, we are in a microscopic regime, so very few atoms, typically if you want a large accuracy, and typically small time scale, ideally basically no time scale at all, if we are just calculating the ground state structure, ground state electronic structure of some configuration of atom. And typically, in order to understand how the system behaves at a realistic condition, we have to bridge to long time scales and larger length scale so that are observable. And on the opposite corner of our atomistic calculations, we have thermodynamics, in which we understand the behavior of a system just with very few variables. On the microscopic regime, we have a kind of full understanding or a full numerical understanding in a way of a system, because we can map the configuration that is, let's say, a point living in a 3n dimensional space into a scalar that is energy. That is very nice. Except that it's too much information, right? If you want to know what are the stable structures and so on and so forth, typically we want to know less information than the full 3n into 1 mapping. And if we want to extract things like temperature, pressure, and so on, we need to find a way to extract this information that is in the potential energy surface, but not readily available. The general framework is to go through free energy. So in given equilibrium of the system, and I will not try to debate too much about equilibrium here because it is a very tricky concept. But whenever one can invoke thermodynamic equilibrium, the system minimizes the free energy, not the energy. And this is a function of certain variables that I will discuss during the talk. So on one end, you have the potential energy surface, and there is some machinery to get out the free energy surface. And in any case, it's a reduction of dimensionality. So you go from 3n to few. And here, when I say potential energy surface can be anything, so can be ab initio, can be force field, or even toy models. I mean, most of the development of computational statistical mechanics has been done on toy models, where toy models, I mean, like Lennard-Jones potential, for example. You can find something that behaves like a Lennard-Jones potential, but typically people use it because it's simple. And the ab initio here justifies why the title of the talk is ab initio statistical mechanics. Of course, it's not the property of statistical mechanics itself that is basically ab initio, but the fact that what I'm normally interested in is the statistical mechanics using ab initio potential energy surface. So more on the side of what can we really do with the slowness of potential of ab initio evaluation, and still get out free energy surface. The sampling problem itself, so why the sampling of an ab initio potential energy surface is low, and what are the problems related to this sampling will be mainly treated by Marianne in the next talk, so she will be talking about ab initio molecular dynamics. Will not really make a huge difference between what is good for ab initio and what not. But certainly I selected methods that are usable, at least, in an ab initio context. Okay, this I've already said. So nature minimizes free energy at equilibrium, and this is important in order to understand phase diagrams. At equilibrium, each phase has the same chemical potential. So by equating chemical potential, whenever we can calculate chemical potential of all the species, then we find the phase equilibria. Sorry, of the phases. Also, by knowing free energy, there should be free energy actually here, not energy. We know also the relative probability to see some structure with respect to another structure. This is most importantly at the nanoscale. And also, we can have also insight into rate of processes. So this is outside equilibrium, but free energy gives insight also into transformation. So namely, a chemical reaction from reactants to products. This is some reaction coordinate. Let's say that this molecule is sticking on these other molecules, so it could be the distance between the center of masses of the two molecules. The reaction coordinate, of course, in this case, it should be decreasing, not increasing anyway. So one has to overcome a so-called free energy barrier, meaning that typically there is an intermediate state that has a higher free energy with respect to the reactant and products. And this is relevant for catalysis because typically people are looking for catalysts that are nothing else than devices, molecular devices, that lower this free energy barrier. Of course, you cannot change the difference in free energy between the reactants and products because it's defined by the reactants and product themselves, but you can change the barrier at will if you understand the mechanism. And the relevant quantity is the free energy. So far so good about free energy. Now, the key thing in free energy is entropy, because on the side of energy, you have heard a lot. We are pretty good. The tricky thing is entropy. What is entropy? So this is a kind of slightly provocative slide, or let's say a different way to see something that you have seen for sure in all your basic courses. So this is the definition of free energy in statistical mechanics. It's the logarithm of the density of state multiplied by a Boltzmann constant. If people were smart, they would have said the Boltzmann constant is 1, and you define free the entropy as basically the scale in this thing. But for historical reason, we have a constant here. In any case, it's the logarithm of the density of state. Density of state is the number of state with a certain specific energy and integrated over all the possible configuration of the system that are compatible with this energy. Now, if you rewrite this thing, if you write the first principle in a differential form of thermodynamics and plug in the entropy, because the dq is T in ds, and then you write all your work as a product of some of the control variable with the conjugate variable that you can always write for any kind of work that you do on the system. An example is like you have the pressure that is conjugate to the volume, so the work done on the system is a change of volume multiplied by the pressure. Now, this sum goes over all the degrees of freedom that are controlling the work that is done on the system. What is left is TdS, right? It's what makes this thing differential. Now, suppose that you can control all the degrees of freedom. Entropy disappears. Because you have done, basically you have put something on each degree of freedom, and then this sum is du. So if you control all the degrees of freedom, there is no entropy. So the entropy is the measure, in a way, of the lack of information that we have on the system, because there is some degrees of freedom that we are not interested in, We are not controlling, and everything goes into the entropy. Okay, so there are many definitions of free energy, and this is not just to remind basic courses, but because normally from each different definition or each different interpretation of free energy, there is a method that is connected to this definition in order to evaluate it. So of course you have the fundamental link between statistical mechanics and thermodynamics. Free energy is minus kT logarithm of the partition function, where the partition function is this integral here. So the Boltzmann factor integrated over all momenta and all configurations. Then typically in classical statistical mechanics, one can do the integral over momenta analytically. So this lambda over to the 3n power, the de Broglie wavelength, and one is left only with this integral that is typically analytically untreatable. So it's an integral of the exponential of the potential energy integrated over all possible configurations. And this is what we are typically concerned with. So in thermodynamics, the free energy is E minus Ts. Simple and good. Actually, if you can tackle the entropic term properly, that's it. You can evaluate the free energy of a system simply. And there is a method that is called ab initio atomistic thermodynamics that actually exploits this fact. So basically with energy and a little bit of reasoning on the system, you get out free energy. Another useful definition of free energy is through its derivatives. So many derivatives of free energy are observables of the system. And actually this is also the way in experiment people would measure differences in free energy. If you can measure the derivative and integrate, and you know the free energy in some reference state, you can calculate the difference in free energy. Then we have the probabilistic interpretation of free energy. The probability that you have a state at a certain energy is equal, well, density of states again, and is equal to this term here. So you have the Boltzmann factor, the number, the density of states, and this normalization that is the partition function. So this is the probability to get a system at a certain energy, in a state of certain energy E. So the absolute probability is difficult to treat because we have this normalization factor that is typically difficult to get out. I will be talk at length about this the partition function, especially in the last few slides. The good thing is that the partition function is a property of the system at a certain temperature. So the probability, the relative probability to be in a state of energy 1 or with respect to be in a state of energy 2 is just the ratio, is just the exponential of the difference of free energies. So this is much more treatable. And you get the relative probability to be on one or the other state. This other kind of mysterious slide is to justify why we talk about a free energy that is the property of a system. So basically, if you are in the canonical ensemble, the system is defined by N, V, and T. Number of particle volume and temperature, and that system in that particular triplet of NVT has some free energy. You have to give the Hamiltonian of the system, of course. But people also talk about free energy as a function of some variable. Because if you have a chemical transformation or something, and you go from one state to the other, you have free energy, and you have this free energy barrier, you have free energy as a function of some coordinate. How comes? Well, it's a bit of stretching of the concept of free energy. So the energy of the system, not the free energy, is a mapping from 3n coordinates to one scalar. Energy has very nice properties. But now, let's look for, or let's define any other mapping from the configuration of the system, so the full 3n vector, into another scalar. You can define the probability that the system has a certain value, zeta, I think, of this function here. And this is given by this integral. I mean, they always look like the same. You have the Boltzmann factor. You have to impose that the system is in this value. So you have the delta, the Dirac delta, integrate over all configurations that are compatible with this value of the variable, and you have the normalization. Now you define this guy here as a new partition function that is a partition function with respect to this mapping function here. And you can define also a free energy related to this partition function that looks exactly like the free energy, the usual free energy, let's say, the thermodynamic free energy. So, and the probability that you get this is again formally similar to the free energy, to the probability to get a system in a state of energy E. So by this formal analogy, you say that you have a free energy also with respect to some coordinate. It's a bit subtle. Normally you don't care, but it's good to see that it has a clear meaning. Other thing that you have in textbooks is always that when you know the partition function, you know everything about the system, right? So I just summarize a little bit of what that means. So you have seen already this expression. The average energy of the system is related to the derivative of the logarithm of the partition function. The heat capacity is also, well, is a further derivative with respect to temperature of the energy, so it is related to the partition function. These are all observable, so you can measure in the system. Or if you know the partition function, you can deduce them. It depends on which way you go. And this is another example. I will not insist too much. Also the pressure, if you know the partition function, can be evaluated directly. You have first to rewrite the integral with the scale coordinates in order to capture the volume dependence. And I put this because what I like is that in this definition of the pressure, there are two terms. One term is the ideal gas, and the other depends on the actual interaction. So the pressure is this term here, plus an average, an ensemble average that you measure on the derivatives of the potential, so basically on the forces. So this is the virial. So the nice thing here is that most of the time when you have quantities that are derived from the free energy, you have this dual thing, the ideal gas term and the Hamiltonian potential energy dependent term. And typically one you cannot evaluate analytically, but you must sample. The other one you can evaluate analytically, and typically you cannot sample. If you try to get this out of a simulation, you will simulate forever before converging it. That means basically that you have to throw particles non-interacting in a box and try to measure the pressure of them just by sampling. That's useless, but also it would be difficult to converge. Now, the way we sample quantities in one way or the other is given by this, again, textbook kind of definition of expectation value of sub-observable. You have the integral weighted by the Boltzmann factor of the observable and normalized by the partition function. Now, the sampling methods are typically based on the fact that you move from one point to the other, so you construct a sequence of points such that you sample the system with the density that is proportional to its density of state, so that you make a simple average of something that samples the system with the density that is proportional to the density of state of the system in order to get the observable, right? So you go from this integral, or from this integral to this sums to this one that is actually what is sampled, so a simple average. If you can sample with the proper probability density. Actually, I skipped this one. I spent too much time. This is about ergodicity, so whether you can go from a sampling over the configurational space into a time average, but I'm pretty sure Mariana will say something about this. Back to free energy. So these things we can treat, typically simple averages over quantities And the trick is that basically the denominator, the partition function, is part of the sampling itself, so we don't care. If we want to address the partition function, we would need to address this integral that is typically untreatable unless we have an ideal gas or a few other systems for which we can calculate it analytically. So we need methods to sample. This is the kind of little zoo that I will present today. Different methods spawning from the different definitions of free energy. And just to give an overview of what kind of weapons you have in your at your disposal when you want to look for free energy, or better, difference in free energies. So we have the analytical way of initial atomistic thermodynamics that actually will be object of part of the lecture of Sergei on Tuesday, so I will not say anything today. Then we have thermodynamic integration from the derivatives, perturbation from the probability definition, and then I will talk a little bit about how to bias the sampling or how to reweight afterwards in unbiased kind of thing. And I will put a stamp of merit that I think can be useful when methods are inherently parallel in the sense that you can do several independent calculations in order to get your free energy. They are good, and while you have to kind of do it in sequence, this is less good because, yeah, you are not exploiting the parallelization that is something we like to do these days. So thermodynamic integration is extremely trivial. You have to start from some known derivative, like the derivative of free energy with respect to the volume is minus the pressure, or this one, and basically integrate. So the free energy, for example, if you take the pressure at a certain volume V, is the free energy at a certain volume V0 plus this integral when you go from V. So what you need is the P expressed as a function of the volume in order to do this integral, and this is known as the equation of state, right? So this is the density of the volume, but okay, you can measure these points for your system, and then you can get out the difference in free energy. You need a reference state in order to compare this to another system, for example, and this could be the ideal gas when the V0 is infinite. That is doable. One has to be careful because, of course, this thing tends to diverge when you go to infinite volume or to zero density. So you have to be very careful in this part here. That's not the very interesting part of thermodynamic integration. We can do in computations thermodynamic integration that follows an unphysical path, and typically this is the most powerful. Unphysical in the sense that or I would say non-experimental or non-empirical, whatever. You cannot typically do it in an experiment, but you can do it easily in a simulation. That is, you define a Hamiltonian that is a linear combination of two Hamiltonians, U0 and U1 with a coupling parameter, and you can go from one to the other continuously. Then, okay, this I try always to write how you derive the thing. You start from the derivative of this free energy with respect to this coupling parameter here, and it turns out that this difference, the derivative is equal to the expectation value of U1 minus U0 in the ensemble with the value lambda. That means that is fixed the value of lambda, you have a certain U lambda, but the derivative is a function of the values U1 and U0 at each sample point. So you can integrate this one. You need a reference, of course. So your U0 must be an Hamiltonian for which you either can calculate analytically the free energy or you can find it in some other way because somebody has done from another U minus 1 to U0 and you know already the free energy at U0. This is fundamental to have the reference, because if you want to do phase equilibria, as I will show in a few slides, you need an absolute reference of free energy. So if you want to calculate the difference free energy between the liquid phase and the solid phase, you need that the zero of the free energy is the same in the liquid and the solid. So you need to have the same, either the same U0 or the same reference. I will show in a couple of slides so it becomes more clear. I will show a kind of fully worked out a calculation of a phase diagram of one species substance in order to show how you can use thermodynamic integration to get phase diagrams. It's a bit involved, but well, you start the simulation, you sit there, and at the end you get the result. There are very few pitfalls, possible pitfalls that you have to look into. So the example is about the phase diagram of carbon that has diamond, graphite, and some liquid phase. Not only, but that was the focus of this work. So the free energy is this one from a reference to the final state, where reference is some Hamiltonian for which we know the free energy. So for the condensed phase, okay, so this is again the same plot. We want to go from graphite to diamond and then include also the liquid phases. So for the solid, we use the Einstein solid, for which we can write the free energy, and the coupling between the Hamiltonian that we use and the Einstein solid is given by the displacement of the atoms in the harmonic potential. So one can measure this displacement in the actual potential and then find the harmonic spring that does it. Okay, it's a bit of technical detail, just to say that one has to try to couple the system as close as possible, and I will show why in the next slide. The liquid, the reference is the Lennard-Jones, for which we don't know analytically the free energy, but people have been looking for free energy of Lennard-Jones liquid like for decades. So you just go to some of the tables. It's similar to the LDA, Seppeli-Adler. So we don't know the LDA, somebody has tabulated it, and there is another paper that is almost as cited as Seppeli-Adler for Lennard-Jones, because everybody does Lennard-Jones, and you have the equation, the free energy of Lennard-Jones liquids. So this is the thermodynamic integration, or at least the derivative as a function of lambda. When going from, so on this side we have the initial, so the kind of U0 reference Hamiltonian, and this is the final Hamiltonian. Don't mind about this name. Is some empirical potential that I was using when doing this calculation. So the constraint or the requirement that the system that is coupled, so this U0 that is coupled to the Hamiltonian that you are actually interested in for the free energy, comes from the fact that you are constantly looking at this quantity, Uref minus U final. So if the two systems are very different, by different meaning that certain configurations with one of the two are completely forbidden, impossible with the other one, you get some diverging energy on one of the two sides here that makes everything diverge, right? So the two systems have to be similar in some way. There are ways to check beforehand that they are similar. Okay, now you have the free energy at one specific number of particles, volume, and temperature, and then you want to find the full phase diagram. First of all, you need the free energy as a function of pressure, because most likely you want to equate the chemical potentials that are function of pressure and temperatures. So to go from volume to pressure, to change the ensemble, you need the equation of state. And you integrate the equation of state, and you get the free energy as a function of pressure of the three phases. Where they intersect, you have coexistence. So at this pressure and this pressure and this pressure, you have coexistence between the three phases. This one is metastable with respect to this other phase, but it doesn't matter. It's still a coexistence. And it is good because from each coexistent point, then you can integrate with the Gibbs-Duhem or Clausius-Caperian. So you integrate the Clausius-Caperian equation that is called Gibbs-Duhem integration, and you can find the phase boundaries. This is the bad part. You have to integrate this differential equation numerically, and you have to do it serially. because you start from points. So these are the initial point that I had, 1, 2, 3, and then integrate here, and integrate here in order to get the full phase diagram. Yeah, compared to some experimental evidence that was pretty good. You see, quite long time ago. Another way to get the coexistence without transforming into the pressure temperature ensemble, staying into the volume, so the canonical ensemble, is by looking at the common tangent of the equation of states. So you have the free energy as a function of volume, and where these two guys have the same tangent, you have a coexistence, and where the slope is minus the pressure. So. And you have seen this already. This was historically the first time a phase diagram was calculated ab initio. Matthias has shown this the first day, Ian and Cohen in 1980. This is at 0 temperature, so the free energy is actually energy. So you get the coexistence at 0 temperature. More recently, the same thing was done like in 2013 to get the phase equilibrium of cerium that has very strange phase diagram with 2 cubic phases that are stable. Well, stable is debatable because one is a negative pressure, but okay, they are at least numerically stable in a calculation. And there are evidences that they exist at least at the nanoscale. Okay, so to me, the real fun starts with thermodynamic perturbation because it starts a little bit manipulating the statistical mechanics, kind of very simple equations. And typically what one does is multiplying by 1 over and over and see what happens. So this to me is a very insightful way to define the difference in free energy between two systems. It is also related to a method to actually calculate this difference in free energy. So let's say we have system 0 and system 1, and you write the partition function for both. As you see, so the momenta is factored out, and you have the potential energy 0 and potential energy 1. The difference in free energy is related to the logarithm of the ratio of the partition function. So this thing here, where already there is E minus beta U0, E plus beta U0, so there is the multiplication by 1. But by doing this simple manipulation, one sees that this difference in energy can be interpreted as what? The expectation value of this quantity here in the ensemble defined by U0, because you have the Boltzmann factor and the partition function here. So this logarithm of the expectation values of E minus beta delta energy measured in the system 0 is the difference in free energy between 0 and 1. So look again at this expression. I'm sampling system 1 with its Hamiltonian in some way. So I'm doing molecular dynamics with the Hamiltonian U0 or something else. And at each configuration, or every now and then, it's the same, I sample the difference between this system that I'm sampling with U0 with some foreign Hamiltonian U1 that is not used for the sampling, but I just sample. What would happen if the system was U1? I collect this, and at the end I have the difference in free energy between 0 and 1. To me, this is very insightful to see what exactly free energy is, or the difference in free energy is. I think I skipped. This is the actual way to calculate the difference in free energy by exploiting this thing. And one can measure, for example, the chemical potential of a species. So just the chemical potential is the change of energy, free energy, by adding or subtracting one atom to the system. And one can calculate it in a nice way using this sampling of the system with the other Hamiltonian while you sample with one of the Hamiltonians. Now, one can push further this multiplication by 1 and discover that one can sample something in one state and obtain information about another state. And it goes like this. So if you have an expectation value in a certain NVT1, and you write it like this, multiplied by some E beta 2, so another temperature, beta is always 1 over kT. above and below. And then you regroup a little bit, and then you discover that this is the same as being sampling at the temperature T2 and measuring these differences between 1 and 2, right? So you get the thing at T1 by sampling at T2 and just by averaging the quantity that you are actually after multiplied by this factor here. So this is called reweighting. That would be nice if you could always do that, right? You do one simulation at one temperature and you get the free energy at all other temperatures, or the value of the some property at all other temperatures. This works, of course, if these things here are significantly different from 0. Otherwise, you have a kind of numerical instability. And these things are significantly different from 0 if the states that are sampled, so the configurations overlap between the two states. So this is the probability to get a certain state with a certain energy with a certain temperature, so this thing. So if you want to get information about something that happens at high temperature, T5, by simulation at T0, and the overlap is very small, it could be even smaller, then basically this will not work because we have 0 over 0, so it will become very unstable numerically. And this gives the suggestion for the next method. Yeah, what if I can kind of bridge things that are not overlapping artificially, but in a way that I can reconstruct? Well, this is called umbrella sampling, because the idea is to bridge two distributions that are not overlapping. Say, well, let's see if I can put some bridging potential, well, I shouldn't say potential now, some bridging device that couples the two distributions. Well, when I want to sample the free energy in this way. And there is little overlap here, so I expect that there is numerical instability. So guess what? What I do is multiplying by 1. So I start from the probability to get a certain value of a certain coordinate in the system, so the usual thing. And now my 1 is a new potential. The difference from before is that now I have an exponential of beta, something that depends on coordinates. It's not anymore like a constant value. And you get this up and down, rework everything. You get a partition function in the new Hamiltonian, U plus W, that is a biasing potential. You see it here. So the probability that the system has a certain value there should be a U here, so with a certain Hamiltonian U, is related to the probability with the system with a different Hamiltonian reweighted by these two terms here. If you need to have more steps to bridge because your overlap is not still good, this can be parallelized. That is a typical method that is used for calculating free energies. The only thing that I will show is how to construct this biasing potential. So if you calculate the free energy out of this probability, you get these terms here, in which you have a constant and the terms that depends on the potential itself. Now, the best solution, the best choice for W is that it is equal to minus the final free energy, because basically this probability here would be flat. So you would sample all the configuration with equal probability. And this is always the best, because there is no part of the configurational space that is visited less and has less statistics, because the probability to get there is smaller. Perfect, except that, yes, the biasing potential is equal to the minus free energy. That is typically the quantity that we want to calculate. So if we knew F, we wouldn't need any method to calculate it. So there are methods to approximate iteratively this free energy. So while you're calculating, you change this biasing potential so that you get close to these flat things. Now I go to the unbiased methods. I give it a little bit more space, relatively to this short lecture. Or let's say this compact full course of computational statistical mechanics in 1 hour. I go to unbiased sampling because, well, I prefer it, and I hope I can convince you that it's preferable when you can do it. The oldest method, and still quite used, is replica exchange. And the idea is to simulate the system at different temperatures. The advantage of simulate the system at different temperatures is that when the temperature is low, the system samples some like local minimum accurately. The disadvantage of low temperature is that most likely it will stay in that local minimum forever. When the system is at high temperature, it can overcome barriers. So when the kinetic energy is such that it's larger than any potential energy barrier in the system, it will fly over the barriers. But it will fly too much, so you will not really focus on how deep are the minima, because most likely you are here and there and there and then there, you know, if these are the lower or higher. So you need also to sample at lower temperature. So if we have a sampling of the system at different temperatures at once, and every now and then we ask to a configuration that is part of the sampling at one temperature if it can belong to a sampling at another temperature, and we actually exchange configurations between the temperatures according to the probability that the configuration can be in the other temperature. Then we have a sampling that is canonical, so it's a proper sampling at all temperatures at once. So this is the probability to accept the exchange. It depends on the difference in energy between the subsystem that you want to, between the two configurations that you want to swap, and the difference in temperature, in inverse temperatures. If you do this over and over, you get a sampling at all temperatures. So this would be different simulation. It can be molecular dynamics, can be other schemes like Monte Carlo that we don't cover in this course. You will see kinetic Monte Carlo, but it's not exactly the same. And these are different temperatures, so you run at different, like 8 different temperatures, and then at some point you try to swap between temperatures. And on and on. So when there is a X year, the acceptance the swap has been accepted, otherwise not. And this very complicated plot is to show that if you look from the point of view of configuration and you run this algorithm, you will see the temperature going fluctuating. It goes up and then down. This is a small snapshot. At the end, it should go up and down many times. So the violet one, for example, has gone to the lowest temperature and goes to the highest, and then it should go over and over. There are a few parameters to tune. The efficiency changes slightly when you change this parameter, but the final result doesn't change. So these are sort of non-determinant parameters. And it's by construction parallel, so very good. What one gets out of this? Well, one can reconstruct probabilities a posteriori. Now, okay, this is just to show a little bit one can do it. The thing is only in this formula. The probability of get a certain value of the coordinate of the system in the simulation one is related to the overall probability by this reweighting factor. The important point is that this coordinate is not decided before the simulation. So you let the system evolve with this natural dynamics if you use molecular dynamics, or if it's natural sampling if you use other sampling. And then you inspect the system and you say, well, let's see what is the difference in free energy between state A and B that you didn't know before the system was run. So the advantage is that you don't put previous information in the system before doing the simulation. While all biased methods, and there is plenty of them out there, require that you have quite some pre-knowledge of the system. And it's never clear how much time you have to spend on acquiring pre-knowledge. So typically the bias is efficient in getting the actual result, but typically people forget about how much sampling you need in order to get the pre-knowledge before you put the bias. Here you get automatically things. I'm not saying this is necessarily faster. It will not be. It will be more insightful because you discover things that you have not put in. And to show quickly application that have been done in my group, let's say that we simulate a cluster of gold 4, and after the simulation, one sees that these two are predominant structures. And then I decide that the variable of control is this angle here, and I get the population of the different phases. This plot shows that if I do a simulation at 100 Kelvin, for example, I see the green dots, so the system lives forever in this basin here, in this local minimum. If I take out the 100 Kelvin simulation out of the replica exchange, I have visited the other structure. This is again the same because, of course, this is periodically repeated. And if you then realize, but there is another structure, so then you can redo the reweighting and calculate the probability to get structure 1, 2, and 3 as a function of temperature out of one single simulation in which you didn't know anything before. This is a more involved exercise with the larger gold clusters in which we wanted to understand at which sizes the gold cluster undergoes from 2D to 3D transition. This is quite a debated topic in the cluster community. And we wanted to spice up the discussion by adding temperature to it, like at what size and temperature the system goes from 2D to 3D. And these free energy plots describe clusters at different size. So this is the same size at two different temperatures. And the coordinates here are a bit exotic. So radius of gyration, you know it. But the second one is a bit exotic. And they were chosen in order to have a good representation. But while sampling with the replica exchange, we didn't know before. We just looked at how many different clusters were present after the simulation. So this is the similarity is by looking at how many atoms are two-fold, three-fold, four-fold, and five-fold. So you get an histogram of population of the different coordination in the cluster. And histogram can be treated as a vector, so you measure distance between vectors where the reference is the lowest energy cluster of this size that was found during the simulation. So it's a kind of very dynamical and learning coordinate. And this will be more topic of Monday's talks, that you can learn descriptors. So the way of describing the system. Here you see that if you know how to describe the system, you can get free energy out of it if you have sampled it properly. And this would be the outcome of this simulation, in which of this work, in which the system undergoes a transition from 2D on this side to 3D to this side as a function of size and as a function of temperature, with a very peculiar behavior of size 11 that comes out of the simulation. So I will not insist too much because I want to go to the last method that is also the latest that has been proposed in literature. So it's not fully established, but it is very promising. So at the beginning I said that there is a problem when you want to directly sample the partition function. There is a problem. This method is the first. Well, there is another method that I have no time to explain here. Historically, the first method that tries to address directly the partition function evaluation is called Wang-Landau. And then there is this nested sampling. So I had to choose one of the two, and I prefer this one. So starting again from the partition function, let's see how this can be conceptually done, because it's very tricky. So the partition function is a function of coordinates here, and then is rewritten as a density of state weighted by the Boltzmann factor and so on. And now we looked at the cumulative density. It is the integral from minus infinite to certain energy of the density of states. And this plot shows, so these are two coordinates of the system, and these lines are lines of equal energy. So the density of states is the area between energy and energy plus delta energy, right? So evaluating this is still complicated, right? You should need to know how many configurations that are compatible with a certain energy, or at least try to estimate them. And this could be in your sampling distance very far away. I mean, two configurations can have the same energy very serendipitously, whatever. So I mean, there is nothing in a configuration that tells immediately what we. So two configuration can have the same energy. So it's not easy to go from one configuration with one energy to the same configuration with the same energy, or to all of them. But then one noticed that this thing, this object, this cumulative density is by construction monotonic, so it can be inverted. And it turns out that if you look at the inverted quantity, it's much easier to evaluate. So this would be the energy of a certain volume of the phase space. So we know the limit. When the energy is infinite, we know the volume of the phase space is the ideal gas, once again. Now let's say that I uniformly sample the configurations in this system. So I will get points at different energies. And if I sample uniformly, and I order a point by energy, and I look at the median, so the point that cuts in half my distribution, I know that half of the phase space is with the point with low energy, and half of the phase space is in the point with high energy, if I have sampled enough, right? I can iterate this. Now I cut, and I sample uniformly from 0 to the cut energy. This would be the next thing. And again, I look at the median, and I cut. And every time I know that I am in half of the phase space in volume. I know the original one, so I know the phase volume. I know the cumulative density of state. I can do whatever I want. How do I actually do that? Well, I have to, the first iteration is easy. I sample uniformly because the cutoff energy is infinite. All the other steps have a cutoff energy, so I have to sample uniformly with this cutoff energy. And that means that I need a scheme to do that. And typically, one uses a simple scheme. I simulate until I don't cross the maximum energy. If I cross it, I apply a bias to go to lowest energy. If I diffuse long enough, the sampling is still uniform. But the key thing is that I always sample at lower and lower energy, and I keep track of how many, which were the energy of this cutoff. This was one of the original application. As you see, the method is fully applied for atomistic potential only last year, so it's very young. And this is a phase diagram of aluminum with some empirical potential. It doesn't really matter at this point. And the good thing is that it got 3 solid phases, fluid phase, vapor phase, so the coexistence lines without any pre-knowledge put on the system. This is still quite intensive simulation, but it is the first time that one obtains such a phase diagram without any input. So, of course, these phases are known, but this was not used, this information, when doing the simulation. Okay, so this is the summary where I close. I do not go through again. The only thing I say whenever a method is parallel by construction, and most of the things that I've shown, except the thermodynamic integration, at least the part in which you do the integration of the boundary lines, so all of them are parallel. If the method is parallel, there is good chance you can use it for ab initio simulation, in the sense that the problem, okay, you need a lot of CPUs, because most likely for each single evaluation you already need quite some CPUs, but then you can parallelize over it. If you can access 1,000, 10,000 CPUs, you can get phase diagrams. The problem when it is serial is that you cannot really do it, right? So I'm not just making things easy that are not. If it is parallel, it is doable. Thank you for your attention.